Good evening. Welcome, everybody. Before I do anything else, before I forget, let me remind you, turn off your cell phones, please, or silence them as a courtesy to your fellow audience members and to our speaker. My name is Craig Jackson. I am an associate professor of mathematics here at Ohio Wesleyan. I'm also co-director of this year's Sagan National Colloquium, along with my colleague, Lori Anderson, who's in the Department of Botany and Microbiology. I want to tell you a little bit about the National Colloquium before we get to our speaker. The National Colloquium was begun at OWU in 1984 and was later endowed by alumni John and Margaret Sagan. Since its inception, the National Colloquium has served as an annual forum to explore issues of national and international significance from multiple educational angles. This year's Colloquium brings together internationally recognized artists, writers, activists, and scholars from diverse fields to encourage a broad conversation on current and future impacts of climate change. A central goal of this year's National Colloquium is to engage the OWU and local community in a conversation on central aspects of this timely and important topic, as well to emphasize the fact that all academic disciplines and divisions, all modes of creative and scholarly inquiry, have a stake in addressing the challenges of climate change. I hope your participation in this conversation will leave you with a sense of how addressing these challenges will require collaboration and communication across disciplines, cultures, and political boundaries. Our speaker tonight has a long history of crossing boundaries, both political and geographic, as well as technical. Dr. Lonnie Thompson is a distinguished university professor in the School of Earth Sciences at The Ohio State University and a senior research scientist at the Bird Polar Research Center. He's one of the world's foremost authorities on paleoclimatology and glaciology. Over the past 40 years, Lonnie and his team have recovered ice core records of climatic and environmental variations from both the polar regions and from low to mid-latitude high elevation ice fields. These ice core archives provide a detailed record of the Earth's climate history over the past 25,000 years. His 60 expeditions have taken him to 16 countries, including China, Peru, Russia, Tanzania, and Indonesia. Thompson and his team were the first to develop lightweight solar-powered drilling equipment for the acquisition of histories from ice fields in the high Andes and on Mount Kilimanjaro. Lonnie's expeditions regularly take him into the death zone, a term mountaineers have for elevations at which human bodies are not able to acclimatize, and life expectancy decreases rather dramatically. Indeed, it may very well be that Lonnie has spent more time in the death zone as a living person than any other human being. Ask a mountaineer why they want to climb a mountain, and they'll likely respond with the same quip George Mallory gave when asked why he wanted to climb Everest: because it's there. I suspect Lonnie's answer would be similar. However, the vague and intangible "it" of Mallory's statement would be much more specific when spoken by Lonnie. Why climb mountains? Because the ice is there. For all his extraordinary work, Lonnie has been given just about every award available to a scientist, more than 40 since 2001. Let me just list a few examples. In 2007, he was awarded the National Medal of Science, the highest honor the U.S. awards to American scientists. In April of 2012, he received the Benjamin Franklin Medal in Earth and Environmental Science. In September of 2012, he was given the Friendship Award from the People's Republic of China. Just this year, Lonnie was awarded the International Science and Technology Cooperation Award of the People's Republic of China. The award was presented to him by the President of China in the Great Hall of the People, the highest honor given to a foreign scientist. Please join me in welcoming Dr. Lonnie Thompson.
Thank you, Craig. Thank you very much. It's a pleasure to be able to speak to you this evening. And I want to talk about climate change, the evidence, and our options. I want to say right at the beginning that it takes a team of people to do this. And we're very fortunate to have a great team at Ohio State, as well as graduate students and postdocs, and of course funding agents. And we couldn't do what we've done without the efforts of many people in these 16 countries where we've worked. You just couldn't undertake these kind of projects. So it's really a very large team that allows this to happen. So what I want to do this evening is to talk, kind of give an introduction to climate change, and then talk a little bit about glaciers as recorders of climate change, and then look at glaciers as indicators of climate change. Evidence for recent acceleration of the rate of glacier loss, evidence for some glaciers that are smaller now than they have been in over 6,000 years. But I also want to talk about the human issues on this. Probably about 6 years ago, I decided it's not the information, it's not the science in question here, it's more has to do with human behavior and why we do anything. And so I went to a meeting of 5,000 international behavior analysts that look at human beings, looking for, okay, what are we missing here? And in preparing for that, I read this article from one of their founding fathers, B.F. Skinner, who was very optimistic about human beings when he was young and middle age. But the time he was 80, he had become more pessimistic about our ability to deal with things that are really important to our future. And there are a couple issues that came to mind that relates to climate. Immediate consequences outweigh delayed consequences when you're talking about us. Consequences for the individual outweigh consequences for others. When it impacts us, we're concerned. When it's someone in Bangladesh, we're not so concerned. And then finally, I want to talk about some of our options and what I see as the greatest challenges in the 21st century. So first of all, if we look at the natural mechanisms that have been impacting climate through time, things like changes in the output of our sun, the 11 to 12-year solar cycle, the 90-year Gleisberg cycle, that energy is very important in driving the climate system on this planet. We have changes in volcanic aerosols, tephras, and sulfates, which can, when they go in the stratosphere, can cool the temperatures at the surface of the Earth for 1 or 2 years after major eruptions. And then there's internal variability in the coupled atmosphere-ocean system, INSOs and monsoons. And of course, if you go much longer time scales, you talk about Milankovitch orbital forcings that drive the climate on this planet. Now, on top of that, we now have the human or the non-natural mechanisms, changes in greenhouse gas composition of our atmosphere, changes in aerosols and particles from burning of fossil fuels and biomass, things like coal, which produce sulfate particles, which can lead to actual cooling, biomass burning, black carbon, which can actually lead to warming in our atmosphere. And then there's also changes in reflectivity, the albedo of the Earth as we clear surfaces for more crops and animals to feed an ever-growing population on the planet. Now, the beauty of models is that they allow you to look at how these different forcing factors would impact us. And if we were to, I'm not sure what I did there. Okay. If we were to look at these, now I'll just look at a couple of them. Here's what you would expect to happen. This is the North Pole and the South Pole, and this is the boundary between the troposphere and the stratosphere. And if you were just looking at greenhouse gases, you would expect the troposphere would warm and the stratosphere above would cool because not as much long-wave energy is getting up there as used to. If you were looking at volcanic aerosols, major eruptions put the material tephra and sulfates into the stratosphere, so it absorbs radiation. You'd expect that layer to warm, and as a consequence, the lower layer where we live would cool. Whereas if you were looking at something happening to our sun, something coming outside of the system, then we'd expect these two layers to warm equally because energy is coming out. And of course, with models, you can put all these factors together and look at what's happening. But then you can go out in the real world and say, okay, what is happening? And so if you do that, and you look at what's happening in our stratosphere since 1958, you can see that temperatures have been lowering, except when we have major eruptions, where we put material up there and you get a short-term warming taking place. But down at the surface, in the troposphere where we live, temperatures have been rising. So this response is expected from greenhouse gas forcing and is predicted by climate models. It is not forced by the sun. it was forced by the sun, both of these layers would be warming equally. So we can look at how the system is actually working. And of course, if we look at the greenhouse gases, the Keeling curve, and it's amazing if you go to our National Academy in Washington, when you go into the entryway on the wall, you'll see this curve because it has had such a tremendous impact. And this year, for the first time at Mauna Loa, CO2 levels reached 400 parts million by volume. And you can see this curve. And even though we've had a number of international climate reports that have come out over the years, the rise of this curve is very uniform and very persistent. So we're on a trajectory that has not changed. And if you look at the temperature records, and it depends on how you choose to smooth these records, 60-month running means or 132-month running means, and you see that the temperatures have been rising, but it's not uniform. There's variability as you go along. And if you get up to the present, you'll see a lot of reports in the newspapers and media about temperatures leveling off. Well, when we talk about climate, we're talking about 30-year averages of weather and variability. But if you look at how the temperatures have changed recently, and if you look at how a skeptic would see this, you can draw these lines that actually show temperatures decreasing. But if you were more a realist and looked at these numbers, this is what you would see in those temperature changes. And probably more importantly, if you look at the temperature changes in the US, the 2012 was 3.25 degrees Fahrenheit above the 20th century average. But probably more importantly is if you look at these different years and you see these extremes up here, this is 2012 way up here, that all of these are in at the end of the late 1990s into the 2000s, except for 1934 here from the Dust Bowl years. But if you look at all the coldest years on record, these are all before the turn of the century. And so you can see this long-term trend that's taking place in temperatures here in the US. So it's very important to look at the balance of evidence, the whole picture of what's happening on our planet. So if you're a skeptic, you may choose to look at this little leveling off in temperatures in this curve, but we have all these other things going on. The decline of sea ice in the Arctic, the mass loss in glaciers around the world, and I'm going to talk more about that. Reconstructions of prehistoric temperatures from our proxy records. We have global sea level rise taking place, and we also have the increasing heat content going into our world's oceans. So there are many different indicators that show that the system is changing. And there's still the natural variations going on. If you look at the output of the sun that we've been monitoring ever since we've launched our first satellite, you can see this 11, 12-year cycle. But you can see we've just come from an unusually low energy output of the sun. So the natural system continues to vary and can have an impact. But I think it's still significant that the last decade is the warmest decade ever recorded in our temperature records on this planet, in spite of these natural variations. So we're fortunate to live on a planet that has many recorders, and you can't talk about all of these, and so I'm going to talk about ice, because that's what we do, and give you an indication of what we can do with that, the history in ice. First of all, you have to have laboratories, and these are class 100 clean rooms in which the chemistry is done. We also do the dust analysis in these labs. And what you'll see when we talk about ice cores, it's really interdisciplinary. We have people working from many different fields in this lab. We have a storage facility where we now have over 7,000 meters of core stored at minus 35 degrees C. It's the only tropical collection on Earth, and I'm going to show you how valuable that record is becoming as we have come forward in time. We also design and build the drills to recover these records. They got to be lightweight, portable systems, so we have to have engineers working with us. So it takes a team of experts to really get these records. I would say one of the things about ice that makes it really unique is that it's not only a recorder of climate, things like temperature and precipitation. If you measure these annual layer thicknesses, you can actually calculate how precipitation has changed through time. And there's not very many recorders out there that allow you to do that. But it also records the forcings of climate in the past, changes in volcanic activity through tephra and the sulfates that can be measured in the ice. The anthropogenic emissions and the bubbles in the ice is a history of the atmosphere. So we can go back through time and look at how CO2 and methane has varied long before humans were on the planet. We can actually see when the Romans started mining, and we can see when lead was put into gasoline, and we can see when the Clean Air Act was passed and the lead was taken out of the gasoline. So they're very sensitive recorders to anything that's in the atmosphere. So there are many different issues you can tackle using this proxy. It's important that it be global. The research on ice cores started only about 50 years ago. So many of the pioneers are still alive in this field. And it started in the polar regions in Antarctica and up in Greenland. And it's spread now through the mountain ranges around the world. So if you look at how we get an ice core, and you out on a glacier, you're going to have snow falling at the surface. As you go down, the density of that snow will increase. So you go up through a layer that we call firn. And then at some depth, depending on accumulation rates and temperatures, it becomes ice. And at the time it becomes ice is when you get the bubbles actually being sealed into the ice body. And the ice varies in thickness from 2,000 to 3,000 meters in the polar regions to 150 to 400 meters on some of these mountaintops around the world. And you can find in the ice isotopes as indicators of temperatures, oxygen and hydrogen, pollutants in the atmosphere, so you can look at anthropogenic impacts in the more recent snowfall. Sea salts, dust, all the thermonuclear bomb tests can be seen as radioactive layers in these glaciers around the world. We know when those tests took place, so we have timelines. The CO2 and methane, and then in the ice itself, you have this history of isotopes and dust and chemicals. And occasionally you have a tephra layer, and in the historical period, you can actually link those tephra layers to known time periods, and you can actually fine-tune your time scale on these cores in doing that. So if you look at the longest history we have, it comes from Epica cores from East Antarctica. They go back over 800,000 years, and this is just two of the parameters. This is carbon dioxide measured in those air bubbles, and this is methane in those cores. And if you look at that history, you can see the Milankovitch, the orbital forcings, 100,000-year cycle. And you see CO2 goes from 180, 200 parts per million when we were under an ice sheet here, and it goes up to about 300 parts per million during warm periods when the ice sheets melt back. So if you look at where we are today, there's no analog in this 800,000-year history, and the concern is where we're projected to be and now in less than 100 years with these at the current rate of increase of these gases in the atmosphere. Now, we don't generally talk about methane. It's very important, but it's oxidized in the atmosphere, and in 10 to 12 years, it's converted to CO2. So we talk more about the impact of CO2 because it has a long lifespan in the atmosphere that's measured in decades to thousands of years. And therefore, it becomes very critical. Because you can say, okay, what if we would stop emitting CO2 today? How would CO2 respond in the atmosphere? So if you were to look at that, you would see that initially it decays quite rapidly, taken up by the oceans and the vegetation, but it levels off such that 100 years out, we still have 33%. 1,000 years out, we still have about 20%. So it affects the climate long term. So once it's in the atmosphere, it will continue to impact the climate. Now, of course, one of the drivers here is population. This is the human population, and if you look at 2012 and you talk about 7 billion plus people, very hard to get a grasp on that number. but it really means that tonight for supper, there were 219,000 more people than there was last night for supper. And if you take a city like Columbus, Ohio, every 5 days, you have that type of population being added to the planet. So these are huge numbers. The other thing that we don't often talk about is what does it take for these people? So if you look at 2012, it required, if we were just looking at animals, 17 billion chickens and ducks, 1.9 billion sheep and goats, 1.4 billion cattle, 1 billion pigs, 400 million dogs, 500 million cats. I mean, we have a huge impact on this planet. And you can say, well, if you contrast this with the pre-exploitation number of American bison, there were 60 to 80 million. So these are huge numbers. And of course, if you look at the Earth from our International Space Station, you can see at night we're lit up, and 65% of that energy lighting those cities is coming from fossil fuels. So they have tremendous impacts. But what's really telling is, if you look out in 2030, what the world will look like. You can see what age you are right now and see what age you're going to be in 2030. But this is what NASA thinks the Earth will look like by 2030. Much different than today. And if the real key here is, where's that energy coming from? What are our choices on that energy supply that we're going to need? And then what is that going to do with the climate of this planet? So I want to talk about some of these records, but only a few. We have, these are the places that our team has recovered ice cores over the last 35 years. And we spent a lot of time in the tropics, because I think we forget that we live on a sphere. And because we live on a sphere, we actually have 50% of the surface area between 30 north and 30 south. We have over 70% of that 7 billion people living in that zone. So it's a very important area to understand how the climate system works and how it may be changing. So if you're looking at sea surface temperatures at the surface, you can see precipitation very much follows those. But when you get up to the 500 millibar level, where all the glaciers are, is a characteristic of our planet. Everything is very uniform, temperature-wise. And that's why we get a very uniform signal from the glaciers in the tropics. This is Quelccaya ice cap. It's the largest tropical ice cap on Earth. And we started working there back in the mid-1970s. If you look at this ice cap, you can, if you go down in a crevasse, you can see these are annual dust layers, because there's a very strong wet and dry season. So you just count these layers, and this is how you get back and set up your timeline. And if you go down in that crevasse and you look at these layers, you can see how uniform they are. And if you measure the thickness of those layers, you can get the precipitation, how precipitation has changed through time. And you can do this over a long period of time. This is what the first solar-powered drill looked like. And the reason we had to develop this was it was a 2-day journey from the end of the nearest road. Everything had to go in by pack animals, and solar panels can be broken down and transported. All you have to have is 40 horses to do that. And you can assemble your power supply to drill. And so that's what we did. And then we went back 20 years later, because in 1983, we couldn't bring back frozen ice core. We didn't have the technology. We brought back 6,000 bottled water samples sealed in wax. And 20 years later, we had the technology to bring back frozen ice core. And so we re-drilled. And when you look at the records coming from the cores, this is a period from 1805 to 1825, just to show two of the parameters: isotopes, which is our temperature proxy; dust. Every dry season where you saw those layers, you got a dust layer. So you just count those back through time, measure those thicknesses, and you have the precipitation or the net balance for the ice field. So here's the core, the isotopes that came back in those bottled water samples in 1983, measured in Willy Dansgaard lab in Denmark. Here's the ice core that came back in 2003, 20 years later, measured on ice here at Ohio State University. And if you look at this history, these are decadal. The reds are warmer periods. This is a little ice age that you see here in these records. And then when you come into the 20th century, you can see the enrichment taking place, the warming in this part of the world. And because you have those annual layers, you can also look at precipitation. And if you do that, these two records are from the summit. This site is 2 kilometers away on the North Dome. But if you look at the precipitation, the browns are dry periods, the blues are wet periods, dry periods, and then the 20th century is wetter than average for that part of the world. So you get this history that's written in the ice. Well, you can go on the other side of the Pacific Basin to the largest plateau on Earth, this is Dasupu. This site is at 23,500 feet. That's Shishabamba in the background. And the precipitation here comes out of India. It's the monsoon history. And it's very seasonal, just like in South America. So when you look at the history here, this is the last 100 years. These are isotopes every year, dust every dry season, nitrates, which reflect what's going on with vegetation, upwind. So again, a very detailed history of the past. And you can look at this back through time. If you take the records out of the tropics and you look at the last 2,000 years, these are decadal averages. The isotopes are temperature proxy. The medieval warm period in here, the little ice age in here. And then what really stands out is the last 50 years in the 20th century. You can compare that to Northern Hemisphere temperature reconstructions. You can see the similarity in these curves, the little ice age in here. Instrumental records in red. And again, what really stands out is what's happened in the last 50 years. So very, very dramatic. Well, there are big systems that work, natural system that works on our planet, like the El Nino Southern Oscillation. And every 2 to 7 years, we have a warm event. And we get this warm water off the coast of South America. By comparing records from the highest plateau to the second highest plateau on opposite sides of this basin, we can look at how these things have changed through time. Now, you think these are in the tropics, but they have huge impacts around the world, and they impact Ohio. For example, if you look at precipitation during January through March, during the El Nino years in the 20th century, you can see there's a bullseye of drought in Ohio from this phenomenon. So even though it's occurring in the tropics, it has huge impacts on the system. Well, with the ice cores, where they're located, like in Peru for Calcaya, when we have an El Nino, this is 97, 98, the deserts of the northern Peru and Ecuador are wet because you got the warm water off the coast and you have lots of precipitation. But down where this ice cap is located, it's very dry. And with these records, you can go back in time and you can look at events that have occurred. This is the isotope record. So both at the top of the Himalayas and the top of the Andes, temperatures have been rising. You can see the enrichment taking place. But if you look at the last 100 years where we have our El Nino historical records, you don't see much. But if you go back to 1789 to 1800, you see a huge chloride event. You get this when you get droughts, major droughts, and lakes dry up. So this is a huge natural event that occurs, and with the ice core records, you can take this back much further. So you can look at the last 1,000 years. These are decadal averages, and if you do that, top of the Himalayas and the top of the Andes in South America, you can see these two big events. Then you can go back and look at human history, what was going on at those times. So if you go to India, this is a map from 1795. This is a famine in 1791 to 92. And in this band, 600,000 people starved to death because of the monsoon failure that occurred at that time. And if you look at this earlier event, which is 1345 to 1370, and you look at what was going on in human history, it's the time of the plague. It's also the time of the collapse of the Yuan dynasty in China because of droughts and famine in that part of the world. So I think that probably climate has played a role in our history long before the 20th century, these natural variations. And we need to know what those are, because you can imagine what an event like this occurring in India today, where we have over 1 billion people, would have on the population in that part of the world. So this is one of my favorite quotes. This comes from A World Without Ice by Henry Pollack in 2009. It says, "Ice asks no questions, presents no arguments, reads no newspapers, listens to no debates. It's not burdened by ideology, and it carries no political baggage. As it changes from a solid to a liquid, it just melts." And I think this is a very telling. You can go to the US Senate and you can talk about isotopes, but you don't get very far with isotopes. But if you can show them what's happening to the glaciers, then it becomes much more real. And so the oldest records we have now of what's happening in the tropics comes from the Quelccaya ice cap. And this is a photo I took when I was a graduate student in 1977. And you can see the history that's in the ice. And this is the same place in 2002. You've lost the history, and you've also lost a very valuable water resource for the people who live in this area. But if you look at the glacier itself, this is the Quelccaya ice cap, Coriocalis, from satellite. This is what it looked like in 1978, no lake here. And by 2011, there's a lake that covers 84 acres. It's 200 feet deep. It did not exist until 1991. And so if you look at 1978 and you morph it into 2011, and I think why this is so real to me is I have had the ability actually to watch this occur. So here we are in 1978, and here we are in 2011. So you can see how the ice is just rising up to higher elevations as this glacier retreats. You can look at this from satellite. Here's Quelccaya, here's Cordillera Vilcanota. This is from 1988. You can look at the same place 18 years later, and you'll see a lot of lakes here. But if you look at the area of ice lost, that's all the yellow places that you see here. And in this 18-year period, we lost 24% of the ice up here in the Cordillera Blanca. I mean, 18 years is not very long. So these are huge changes. This glacier retreats, and this is the ice cap that keeps on giving when it comes to science. Back in 1977, you see people here. This is now a lake in here. This is the backside of that lake in 2002. And you can see a person for scale. This wall is 30 meters high, retreating. And at the base of this wall, we found a wetland plant, perfectly preserved, no woody tissue. And we were able to sample that plant. And it's Titua muscoides. This is what it looks like. This is where it was coming out. You can see the ice wall right behind this guy. And it's 5,200 years in age. And it tells us this ice cap hasn't been smaller for 5,200 years. Otherwise, these plants wouldn't be there because they start decaying as soon as they're exposed. And if you look at that wall, this is 2002. 3 years later, this is the plant deposit. Here's the plant deposit, and you see where the wall is. So we've continued to collect plants, and we have collected over 60 of these, and we carbon date those plants. And just this year in Science, we had a paper where when I first started working here, the ice was here, and all the plants we collected over here are 4,700 years in age. But the ice continued to retreat, and then in 2011, there was land over here. The plants on this side of the lake are 6,300 years in age. So we can look at these ages, and we know that 6,000 years ago, it took 1,600 years for the ice to move from here to capture the plants here. It's taken 25 years for the ice to move from here to here. So it gives you an idea of the rate of which the change is taking place. Of course, you can go around the world and you can look at these photographs, and when you look at them, just remember that the ice is just water on land. When it melts, it goes in the rivers, and it leads to sea level rise. This is the Mur Glacier, 1941, over 800 meters thick in this valley. This is 2004. If you go to the Himalayas, it's hard to find old photos, but here's from the Royal Geographical Society in 1921. You can see these peaks here. This is the same place in 2009. And you see the lake here, and you see how much ice has melted out of this valley. And that's all now in the world's oceans. The Alps, 99% of the glaciers in the Alps are now retreating. This is 1903. This is where the ice was in 2005. If you go to the third pole, this huge area, there are 46,000 glaciers here, sometimes referred to as Asia's water tower. It's the source, these glaciers source many of the major rivers in this region. They sustain 1.5 billion people in 10 countries. And you can take a river like the Indus River. 40% of its water in the dry season is coming from glacier melt. And that river flows through 3 nuclear power countries, China, Pakistan, and India, all depending on the water in that river. So these become geopolitical issues as these glaciers shrink. And I'm going to take you to one of these, Nanunami, which is at the source of the Ganges, the Brahmaputra River, and the Indus River. And so if you go out there, this is what the mountain looks like. And if you make your way up through these canyons and you get to the top, this is the top of the mountain, and you can see the drill camp out here. And we drilled 3 cores to bedrock. Now, one of our big challenges is how do you keep these cores frozen? You can bury them in the surface of the glacier while you're drilling, but then you have to transport them. And just to give you an idea of how that's done, initially Sherpas and porters, these are meters of core. But when you get down here to the edge of the glacier, you're still 4,000 feet from where the vehicles can come out on the plateau. So then you have to go to a local transport system, which are yaks in this part of the world. And these are insulated boxes. There's 6 meters of core in each of those boxes, 12 meters to a yak. We drill 500 to 600 meters. So you got to have a herd of yaks that are moving the cores down to the trucks down on the plateau. Then there's a dash across Tibet to Lhasa, because in Lhasa there's refrigerators. Then there are air cargo to Beijing, clear Chinese customs. Air cargo to Chicago, clear US customs, go into a freezer truck and come down to Ohio State. So the cores are usually in transit for a month from the time you leave the field site. But the first thing we do when we bring them back is we look at these radioactive layers. The first one we look at is the beta radioactivity from the 62 Soviet test in the atmosphere. All the previous sites that we had drilled in Tibet show this layer. But from Nanunami, you don't see it. And then we look for an earlier event, the Ivy test. The Ivy test, this is before we understood the dangers in nuclear testing, and it was done at sea level. So it produced radioactive chlorine-36. And you see it in glaciers around the world. But you don't see it in this Nanunami glacier. And the reason you don't see these is above 6,000 meters where these cores were drilling, they're now losing mass from the surface down. So we're losing that history from the top down. And just a month ago in Nature, there was a report that 2 other glaciers have now been found, one in southern Tibet and one in central Tibet, where these radioactive peaks are not preserved. So it's not just one glacier. And the question is, how many of those 46,000 glaciers are now losing mass from the surface down? If you go to Kilimanjaro, and if you want to see the glaciers there, you should go sooner than later. This is glaciers that were on the mountain in 1912. This is what it looked like by 2006. And we've been monitoring that ever since we drilled there in 2000. The latest aerial photos we had flown were in January this year. And since 1912, we have lost 88.3% of the ice on the mountain. And since we drilled there in 2000, we have lost 40% of the ice that was on the mountain. And here too, the glaciers are shrinking not only aerially, as you can see in these photos. This is Furtwanger that's in the crater in 2000. This is 2006. And by 2007, you can see it split in 2. And as you expose more of the dark surface, you absorb more radiation, and you get these positive feedbacks, and the glacier disappears faster. This is a stake that was put in 2000. This is the same stake by 2004. So you can see it's losing mass from the surface down. And if you look at Furtwanger in 1999, when we first went there, and you look at the same glacier in 2012, you can see it's not only shrinking, but it's decreasing in elevation. And when we drilled there in 2000, we put a stake all the way to bedrock as a drill stem. And we've had people, Doug Hardy from the University of Massachusetts, has been going back and measuring that stake. And this, just 2 weeks ago, this is where the drill site was back in 2000. This is, you can see the ice is totally gone. And this actually shows the decrease in thickness of the glacier over that 13-year period before it disappeared. Furtwanger will be totally gone by 2017, so in only a few years. So the last place on the glaciers I want to take you is to New Guinea. Most people don't realize there's ice in New Guinea, but in the middle of the tropical rainforest, there's a glacier. This is what it looked like in 1936, by 1991, and 2001. And if you look at the satellite images, Landsat 5, this is 1989. All the blue areas are the glaciers here. And 20 years later, in 2009, you can see how much they've shrunk. And this is the only glacier where we've drilled where it rained every day on the glacier. My tent sat here for 2 weeks. The surface lowered 30 centimeters in 2 weeks. And if that's any indication here, we're losing over 7 meters of ice thickness a year. And where we drilled cores to bedrock here, it's only 32 meters thick. So if you look at and you project these out to the future, it's the black dots here, you can see we're looking at these glaciers disappearing by 2017. So just in a very short period of time, as will the glaciers over on Kilimanjaro, if the rate of ice loss continues as it's been seen. Well, we're also losing ice in the polar regions. You've all heard about the sea ice. This is its mean position from 1979 to 2000, this pink line here. This is what it looked like in 2012. And one of the things that concerns me is that scientists are, by and large, very conservative people. And if you look at all the model projections of how we were going to lose sea ice going forward in time, this the mean is this black line you see here. And this is actually what's been happening. So the rate at which the ice is being lost is tremendous. Now, if you're a skeptic on climate change, every time you have a year where the sea ice comes back, you'll see reports that, oh, it's not an issue. And certainly when you come up to 2013, you saw lots of reports in the newspapers about suddenly the sea ice has come back. But if you're a realist, this is how you would look at that curve. So you need to look at the longer term trend of how things are changing. Now, if you go to Antarctica, you'll see that there's a different story in Antarctica when you talk about sea ice. This is what it looks like in the winter, and this is what it looks like in summer. So there's huge seasonal change. But if you look at the history of the loss of sea ice in the Arctic, you get this curve, and you can see that we're losing it in the Arctic, but there's actually been a slight growth around the Antarctic. But you have to look at the numbers. The growth here, the loss of sea ice in the Arctic is 3.5 times more than the growth that you've had around Antarctica. Now, sea ice doesn't, melting it or growing it doesn't change sea level because it's floating out in the ocean. But in the Arctic, the sea ice decrease is tied to widespread warming in the Arctic, whereas in the Antarctic, sea ice increases are, we think, perhaps tied to atmospheric circulation. The storms, this continent is isolated. It has a circumpolar vortex, both in the ocean and in the air around the continent. The most important thing to look at is what is happening to the ice on land in Antarctica and in Greenland. So if you look at the contribution to sea level rise, you can see Antarctica is losing mass, the glaciers on land, which will cause sea level to rise. less than we see in Greenland, which is this curve, and of course the combination of these two is your actual contribution from the polar ice caps to sea level rise. So over the last 19 years, sea level has risen 11 plus or minus 2 millimeters. It's about 0.6 millimeters per year. But the rate of ice sheet mass loss has accelerated from 2005 to 2011. It's now, we're losing, sea level is rising about 1.8 millimeters per year. So about 50% of the current rate of sea level rise, which is 3.3 millimeters per year, is coming from these big polar ice sheets. The rest is coming from mountain glaciers and the steric expansion of the ocean as it warms. So sea level is rising, and we're losing mass from Antarctica as well as from Greenland. So the recent rapid melting of glaciers is worldwide. So climatologically, we're in unfamiliar territory, and the world's ice cover is responding dramatically to these changes. So you can say, what if we lost 8% of the ice that's now on land? I showed you pictures down in Peru, where over the last 18 years we've lost 24%. So I don't think it's a big number to consider. But if you look at the Gulf Coast, this is what we look like today. If we were to lose 8% of the ice on land, this is what it would look like. So here we are today, and this is what it would look like. So how to manage a world with threats from climate change, rising sea levels, and rising energy consumption. To me, these are the big issues that we face in the 21st century. You can argue that there's a perfect storm brewing, and that storm comes in the form that the fact that CO2 has lifespans which exceed 100,000 years once it's released to the atmosphere. There's a climate system inertia. It'll be 20 to 30 years before we see the response to the CO2 levels in the atmosphere today. There's this positive amplifying feedback. As you remove the ice, you expose darker surfaces, more solar radiation gets absorbed, and we have a fossil fuel addiction globally. You can look at alternatives, a brighter future, lower cost fuels, clean air and water, economic development, and good jobs. I think we forget that in this country right now, we have 80,000 miners working coal mines. But we have over 100,000 people now working in solar energy in this country. So there's a change that's afoot and taking place. Now, the thing that gets people's attention are extreme events. And I want to talk just a little bit about these, and especially in the past few years. It's S5 tornadoes that we've been having. This is 2011. Now, not one of these single events can be tied to climate change. It's when you're looking at the bigger picture and you're looking globally that you become concerned. 2011 here in Ohio, it was the wettest year on record since we've been keeping precipitation records in this part of the country. And this leads to floods, and often we don't have the resources to manage the damage to those, and therefore we go to the federal government. Fatalities related to weather. If you're in the life insurance business, this becomes an issue. This is in 2011. These are a number of fatalities from tornadoes and heat waves and weather-related events. And these are the 10-year averages and the 30-year averages. So you can see how these numbers are jumping. And of course, these events are not just in the US, these are global. This is Pakistan in 2011. And if you go to Munich Re, which is an insurance company that insures insurance companies like Nationwide in this part of the world, they see these numbers. In 2011, the overall losses were $148 billion, of which $55 billion was insured. The rest was picked up either by the individuals impacted or by their governments to cover those costs. And of course, in this country, these superstorms like Sandy, over $60 billion worth of damage, 110 people killed, and things that we don't think about. The fact that within half a mile of the coast of New York and New Jersey, there are 45 Superfund sites, toxic waste, that are now subject to these storm surges that we have during these major storms. And of course, when winter comes here and it gets cold outside, you kind of forget about the bigger issues of climate change. But summer comes to the southern hemisphere, and in the southern hemisphere, they've had major fires. This is a fire in Australia, and if you look from satellites, each one of these is a fire. And last year, for the first time, they had to add 2 new colors to their weather map in Australia to cover the extreme temperatures in that part of the world. And then, of course, you come back to the U.S., the number of fires in this part of the world. This is the Rim Fire in August of this year. But what's really interesting is when you look at the millions of acres that have been burned, 2006, 2007, 2012, 2013 will be right up there because we've had huge fires again this year. Very huge impacts. And then these extreme events, a 1,000-year flood in Colorado, not very long ago. And this is an area that they don't have flood insurance because it doesn't flood there. So most of this $2 billion of cost is not covered by insurance. And so this brings to these human nature traits. Consequences for the individual outweigh consequences for others. If it's not in Bangladesh, if it's in your backyard, it becomes more real. You see it, or people that you know become impacted by it. And this is just October 29, 2013, when the storm hit southern England and Europe. This is a lighthouse on the coast of southern England. That's a wave, the ocean, crashing against. I mean, nature is very, very powerful. And then if you come to today, Typhoon Haiyan, death toll is going to be in the thousands. We don't know yet because it's unfolding as we speak. The damage will probably be over 14 billion, but only about 2 billion is insured because people in that part of the world don't have insurance. And so it ends up with the country, and other countries will cover the cost of that. And you look at the damage from these storms. I mean, it's tremendous. And and particularly this city, Tacloban, where you had a storm surge that came in with the typhoon, and which really does tremendous damage. So if you're in the insurance business, you look at these numbers, and this is from 1980 to 2012. These are weather catastrophes around the world, and you can see they're coming from storms and floods and droughts and fires, forest fires, and you can see that they're rising. And if you look at another human behavior, immediate consequences outweigh delayed consequences. When it starts costing you now, then we become concerned about these things. And if you look at the cost, the blue curve here is insured losses, and this curve, the greens, are uninsured. And this is where we had Katrina hit New Orleans. You can see how it spiked. So these events, but we're averaging maybe $100 billion loss a year weather related. So these do matter if you're in the insurance business. So if you look at what our options might be, and I really think we're down to 3. Back in 1992, when I first testified on this subject in the U.S. Senate, I talked about prevention. I don't think that's any longer an option. I think we can talk about mitigation, which means taking measures to reduce the pace and the magnitude of the changes in global climate that are caused by human activities. And examples of mitigation include reducing emissions of greenhouse gases, enhance the sinks of these gases, take them out of the atmosphere. We can talk about geoengineering to counteract the warming effects of greenhouse gases. I mean, these are the options that are out there when you talk about mitigation. Adaptation, which means taking measures to reduce the adverse impacts on human well-being that result from climate changes that do occur. Examples of adaptation include changing agricultural practices, strengthening defenses against climate-related diseases, and building more dams and dikes. But it's a moving target, and we're not very good predicting regional impacts from climate change. And the third is suffering, and that's the adverse impacts that are not avoided by either mitigation or adaptation. And I think if you think about this, these are the things that are really, really on the table. So evolutionary theory teaches that it is not the strongest of a species that survives, nor is it the most intelligent that survives. It's the one that is most adaptable to change. And when we talk about individuals, groups, and nations, in contrast to evolution, we can understand our circumstances and deliberately make the appropriate changes in policies in order to improve the outcome. I mean, we can make those changes. And if you look at some of the things that are underway, conservation, increase in efficiency, 4 cylinders and hybrid cars soar in popularity, electric cars, we can look at renewable energy, fuel cells, zero emission coal burning power plants. We can look at solar, photovoltaic and passive solar, geothermal, recovered energy power plants, ethanol, wind power. We can look at mass transit, light rail, buses, a way to get people around. Housing design toward more compact cities so we don't require so much energy. And nanotechnology and LED technology, all of these things can keep our lifestyle but reduce the amount of energy is required. And I wanted to say just a few things that we're doing at Ohio State on sustainability. One university, one community, and one planet. We have now 70+ student organizations that focus on sustainability at Ohio State. We're number 3 on the US EPA's list on the 20 largest university users of green power. 25% of our electricity comes from wind power. We just put in a geothermal field to heat and cool our dorms. Ohio Stadium, we set a national record by diverting 98.2% of the waste from landfills in 2012. 7.1 million in energy efficiency and conservation infrastructure to upgrade 5 campus buildings. 37 alternative fuel buses on campus. The university's goal is to divert 90% of the materials generated on campus from going into landfills by 2030. We have now 7 charging stations available for electric vehicles. And in 2012, we planted 916 trees. So there are a lot of things that you can do on this. But I want to close by telling a personal story, because it really, of all the things that have happened, it really allows me to understand skeptics much better than I have in the past. For 20 years, I was treated for exercise-induced asthma. And in 2009, I was diagnosed with congestive heart failure. And my cardiologist looked at me and he said, Lonnie, he said, you're going to be on a plateau. And he said, you're going to drop to another plateau. And out here, your only option is a heart transplant. And I said, you're kidding me. I've been at 23,500 feet. I've climbed all of these mountains, and you're telling me I'm going to have to replace my heart? What do you know? And so I fought him for 2 years through a defibrillator. And then when I was drilling in the Alps in 2011, I just could not breathe. And it's only about 14,000 feet, so it's not really a high elevation site. And I ended up getting back to the Ross Heart Hospital, and sure enough, I ended up with a balloon pump, which sustained me for 5 days. Got a terrible infection. They told my wife and daughter that I wouldn't live 24 hours, but I did live, and they put in an LVAD, which is a left ventricle assist device that was only invented 6 years ago, which is a turbine. They put in the old heart, and I had a drive line, electric line, coming outside, and I ran on batteries during the day, and I plugged into the wall at night, and this was my bridge to get on the heart transplant list to get a heart. And so when I went to get the Benjamin Franklin Science Medal, this is my wife and I, you'll see that I'm running on a computer. There's batteries under my coat, and when I came back from this, 4 days later, I get the telephone call that they have a heart for me. And I was in the Ross Heart Hospital at the university and was very fortunate to get a heart. And 1 year later, I led an expedition to the Zangser Glacier at 20,500 feet in western Tibet. Now, there's no other time in human history where you could recover these ice cores and someone like me could still be standing here talking to you. But the lesson here is that when you talk about climate change, just like when I was talking to a cardiologist about my condition, and he's a cardiologist and I'm a climate scientist, it doesn't really matter what we believe. At the end of the day, it's only what is, and what is what we deal with. And I think that will be the case when we talk about climate change. And when I look at the future, I think the 21st century, we have two major challenges. Learning how to get along with each other on this planet, and you can argue how well we're doing that now. But learning how to get along with on which we all live. These two challenges deal with human behavior, and they're closely related when you look out into the future. So if we learned anything from our International Space Program, it's how unusual this planet is to sustain life as we know it. And when we talk about global climate change, nature is the keeper here. None of us can see the clock. We don't know how much time we have to make the changes. But we do know that that clock is ticking. And so with that, I'd like to close, and I'll be glad to address any questions or comments that you might have. So thank you very much for your attention.
If you have questions, I'll come around and give you the mic.
Hi, Professor Thompson. So you said that mitigation, one of the options was to have geoengineering. And as you know, in the 1950s, Roger Revelle said we're doing an unprecedented experiment with the planet. And I worry about using geoengineering because once we start, we probably can't stop, and we really don't necessarily, right now anyway, know exactly what we're doing if we were to try to engineer the planet. I mean, we are engineering the planet, and look what we got.
Yeah. No, I think that's absolutely correct. And in fact, it was at a conference with Sherry Rowland before he passed away, and he said that if we ever got into geoengineering and our research proposals to NSF, now you're evaluated as excellent to very good, good, fair, and poor. We'd have to have dangerous and very dangerous as categories. But on the other hand, it is, I believe that if you look at our projections on our models, in most cases we have under-predicted the actual response in the system. And what if we wake up one day and find that there's a huge change that's taken place that none of us anticipated? Would it not be wise to have at least thought about the possible ways that you might geoengineer the planet? I don't think we should be implementing any of those things because, as you say, we don't really understand all the connections and the unintended consequences of those type of things. So it's a very good point.
I was interested in your map that showed all of the rivers in India and that area that depend on the ice cap. If we slowed the melting of those ice caps, would that mean that there would be less water in those rivers and thus less water that was necessary for that civilization or civilizations?
Well, I think that's an important question because if you look at countries like Peru or that part of the third pole region. The glaciers have been there for thousands of years and they've built up an archive of water on these mountaintops. And you could make an argument that in many of these countries, the developments on those rivers in the last 100 years have been based on unusual amount of water flowing because of these glaciers melting and adding to the normal discharge on the rivers. So you may have actually built populations that are unsustainable if these glaciers weren't there to melt. But it's like taking money out of a bank account where you're not putting anything in. Eventually, you don't have any resources. And if you take a country like Peru, where 76% of their electricity comes from hydropower. It depends on rivers coming out of the Andes, coming from the glaciers. And that in a region where you have a very marked wet season and a very marked dry season. It's that 3 months when you're not producing hydroelectricity that you're in trouble on the grid. And as a consequence, they're building more fuel-burning power plants to make up for the lack of power on that grid. So you get into these loops that only make the situation worse, but it's a good point.
Thank you very much for the incredibly informative talk. One of the things that I was struck by was learning so much about the process of the coring. And I was curious if you could say a bit more about the time on glacier and how long it takes to use the solar drill and get those samples.
Well, a typical expedition will last anywhere from 6 weeks to 2.5 months. The power source is important in some areas where you could. The beauty of solar power on a tropical mountain is that each of those panels performs 20 to 30% above manufacturer specs because you have over half the Earth's atmosphere below you. So they're a wonderful source, but you have to be careful. All of our drills are DC driven, and so when we start in the morning when the sun comes up, drilling is slow. The maximum rate of drill is at noon in the tropics, and you have to make sure you get your drill up before the sun goes down over the next mountain range, or you'll lose it. So you have to adapt to that. But to drill 168 meters will take you about 18 days using solar. The beauty of using a diesel or gasoline generator in areas that are very cloudy is that you can work day and you can work at night. So you can reduce the amount of time your team has to spend on top of the mountain. And there's not a lot to do when you're up at 20,000 feet, so you might as well work and get the job done and get the cores up. So it takes a special group of people. I mean, most engineers would not go and work at these elevations, so I feel very fortunate that we have a great team of people that have allowed us to do this over the years. And we've identified people around the world. We don't keep all these people at Ohio State. When I have a project over in the Himalayas, I get on the phone and I call people in South America and over in Russia, and I say, we're going to meet in Kathmandu, and we're going to go into this ice field. And we all come together on a certain day. We know what our jobs are, and we go do it. And also, it gives me a lot of encouragement in the future because our teams are international. We have Chinese, Americans, Russians, South Americans, all working together on an objective and under very extreme conditions. And we succeed at that. So I am absolutely sure we can, as a people on the world, work together to solve these issues that you see here. And I don't want to make this negative because I showed you what the world will look like in 2030 or NASA's view of the world. I mean, 80% of the energy we use to light the streets go to space for no purpose. I mean, you can think of how much energy you could save by just putting it where you need it. And so there's a lot of things that we can do as humans when we come to the point that we have to do it. I think humans are very good when your back's to the wall, you have no other choice. We're pretty good about doing the right thing, but it's only when we have no other choice.
Was there an event or an observation that brought you to this research initially?
Well, that's a good question for young people because, you know, you start out, I grew up in a very small town in central West Virginia. And there was 2,500 people there when I grew up. There's 950 there now. First child to go to university from my family. And I went to Marshall University, and I studied physics to start with, because I knew I wanted to be a scientist, I just didn't know what scientist. And when I was a junior, I took a geology course. And I really got interested in big processes, big things, and working outside. You don't have to sit behind a desk all the time. And so got a degree there, and I actually went to Ohio State to do my master's studying coal geology, because I was looking for a job. And we had one of the world's experts in coal geology at Ohio State at the time. But my first quarter there, I got a note in my box saying that there was a position available in what was then the Institute of Polar Studies to look at ice cores. And I thought about that, and I said, yeah, I'd had geomorphology, and glaciers only cover 10% of the surface of the planet. They're in places where people don't live. How could they possibly be important? And more importantly, how could you ever make a living looking at ice? And, but it was a research position, which meant I could get my degree faster and get out there and get a job. And I took that, and it took about 1.5 years to start to realize what was possible in the archive in these cores. And so there's no way in the 1970s, mid-70s, that I could have seen the importance of this field. There were very few universities that had a professor in glaciology. It was a very boutique subject, but only, I think it was 4 or 5 years ago, University of Michigan hired 5 glaciologists at one time. So the field, the importance of ice is now seen around the world, and particularly as it relates to sea level rise, and understanding ice processes. But when you start the journey, you never know where it's going to lead.
Other questions? Oh, our organizer has a question.
I was curious to know what your view is of your field now. Like, where is there a paucity of data, or what are the most important things that ice core researchers need to focus on in the future, given climate change issues, and what can still be learned from ice archives?
Well, I think it's an important question. One of the things that we see, one of our missions is a salvage mission, to get these records from places where they're going to disappear and getting them in the freezer. We keep half of the core for the future, because we know that 20 years from now, a lot of these places, you're not going to be able to go out and get the records. But there'll be new technology, new understanding, but you'll need a sample to investigate. So salvage, getting those records before they disappear. But in the ice itself, the field is 50 years old, which is very young. And to me, I see future in looking at climate and health, human health. These events, like I showed you this 1345 event, the plague, it started from bacterium in soil, and it vectored to mites, from mites to fleas, and from fleas to rats, and from rats to humans. But something set off that sequence of events, and what the role of climate is in those. Or if you look at influenza in 1918, 50 million people died from that. It was one of the biggest El Nino years in history. Only 16 million people died in the First World War. And you look at medical papers, there are people looking at, doctors looking at migratory paths of birds. And when you have changes in wind fields on the Earth, birds that don't normally come into contact with each other suddenly come into contact with each other, and you can have diseases that can come into play when that happens. So, but understanding those type of things. And I think in the ice itself, there are microorganisms. There's looking at biodiversity, and at least 75% of the biodiversity on this planet is in microorganisms. And in the ice, you have a frozen history of these. There are very few places on the planet where you can find microorganisms and DNA frozen in time. And so I think there's a lot that can be done there. I always tell my students that there's a lot of opportunities for the future, but they're not the same opportunities that I had. And so I think that we're only limited by our imagination of what we can do with the various archives that are out there. Another big important part will be bringing all those archives from marine cores, sediment cores, corals together to understand how the climate system works. And so I think there are plenty of opportunities in this area.
I have a question. Speaking of future opportunities for future research, can you talk a little bit about the possible ways in which the practice of science has perhaps changed over your career to address some of these complex multidisciplinary questions, or ideas for how future scientists are going to be best trained to work well with others to address some of these complex questions?
Yeah, I would say that we're always trying new things. I teach a class in paleoclimatology, and I teach it at Ohio State, and at the same time I teach it in Beijing, China. The students in Beijing, China come to class at 10 to midnight. It's real time, and we usually have 20 graduate students attending that class at night. When I look at the future, I don't think as a country we will be able to do science as we have in the past. I think that when we look at big projects, expensive projects, there's going to have to be a collaboration between countries to share costs so that science can be done. And we actually interact with the Naval War College up in Rhode Island. And the Navy has no qualms about climate change. Where there used to be ice, there's now water, and they are most vulnerable to sea level rise because all their strategic bases are at sea level. And so they are asking questions like, what do we need in tomorrow's world in the way of ships? Do we need to have more hotel ships? Hospital ships to evacuate people from damaged parts of the world. And these are big questions because in everything there's a lag time. You have to get a congressional approval. Try that to build a ship, and then you have to get a shipyard to build it. And so there's a timeline to responding to these things that are built into our institutional structures. But I think that the problems are very complex, but I think we have, with technology, I see the future in virtual institutes. You have a major question that needs to be addressed. You bring people, the best people in the world together to solve that problem. And then when you solve that problem, you may rearrange to solve another problem which requires a different group of experts. But they don't all have to be at the same institution for that to happen. So I think I look at Ohio State, some of the things that we're doing. We're looking at hiring people across disciplines that can look at the interactions between fields. And because if you look at, most people believe that the big breakthroughs in science are going to come in those interfaces between disciplines. And that takes building a culture that allows that to happen. But I see evidence that that's actually taking place. Yeah, but it's an important question to ask.
Any other questions for Dr. Thompson? Well, let's thank him again.
Thank you very much.